Okay students, welcome to another video, and this will be a small video regarding the electrical characteristics of sequence currents. So the topic is electrical characteristics of sequence currents. Electrical characteristics of sequence currents. Now we know this thing, that electrical unbalanced currents can be converted into positive, negative and zero sequence currents. This we have already discussed, and these are the, let's say, IA, IB, IC positive sequence currents, right? Plus this is positive sequence, and then we have IA, IC and IB, and these are the negative sequence. And then finally we have the zero sequence, right? Now what is the significance? We have discussed that, okay, this is 1, 1, 1, 2, 2, 2, IA naught, IB naught and IC naught. Zero sequence. We have done all this, and we have also discussed, okay, how we convert this and how from one sequence to phases and from phases to sequence. Now the question is, what is the significance of these two currents, of these three currents? Now one thing that you will notice, and this we have discussed also, that for positive as well as negative currents within a set, the magnitudes are same, and the angular separation is also same, which is 120 degrees. So if we draw these, let me draw it. With respect to time, right? I am drawing a positive sequence at the moment. Sine wave, right? And then comes the second one with 120 degrees phase difference, and sorry for a bit of irregularities in the drawings, and then comes to 40 degrees phase difference, right? We extend it, it will become like this, and this one will be like this, if I'm not wrong, right? Now you can see that at any instant of time, the sum of these three phases is equals to 0 due to this 120 degrees phase difference. I say, okay, that I am taking a time t1. At this time t1, the yellow and blue phases are negative and the red is positive, means their sum will be 0. At time t2, blue and red are negative, yellow is at maximum peak, right? Sum will be 0. Similarly at time t3, 2 negative, 1 positive. Even at this time, yellow is at negative peak, red and blue are positive. This means that the sum of sequence currents at any instant of time, and I am talking about the positive and negative sequence currents. Why? Because they have the 120-degree phase separation with them. This means that I0 plus A plus IB plus IC, whether it is of positive or negative, this will be equal to 0. What I am saying, IA1 plus IB1 plus IC1 at any instant of time will be equal to 0, and same is for IA2 plus IB2 plus IC. So this will also be equal to 0. Right? Now this means what? We have already seen that at any instant of time, one phase is getting positive and the other two are negative. This means that for positive and negative sequences, each of the three phases, or you can say all of the three phases, are acting as the incoming as well as the return path as well. At an instant of time when the current is incoming through phase A, then yellow and blue are negative. This means the same current is returning from yellow and blue phases. Similarly, when the current is incoming from phase blue, then red and yellow are acting as the return, and same is the case. This means that for positive and negative sequence currents, the three lines serve as the incomer as well as the outgoing line or return path as well. There is no separate return path needed for the flow of current for positive as well as negative sequence. Why? Because the 120-degree phase difference accounts for the return path as well. Clear? And now comes the very interesting part. Let's draw the zero sequence. After all, it is a phasor. But here, this is red, this is yellow, and this is blue, which means that when one is positive, all the three, the second one is also positive, the third one is also positive. And when they are negative, all the three are negative. This means what? The zero sequence current needs a separate path for current flow, because at any instant of time, all the three phases are causing the current to inflow, which means it needs a separate path, and this separate path is served by neutral. Always remember, in delta connections where there is no neutral, only three phase currents are there. Only positive and negative sequence currents can flow. Why? Because in delta connection there are three lines, and positive and negative sequence currents require three phases to flow, because 120-degree phase angle accounts for the flow, inflow as well as return path. But for zero sequence, you always need a neutral as a separate return path. Why? Because there is no phase difference among the phases. There will be no zero sequence current in the delta connection. We know that now, once we have decided that okay, the neutral carries this zero sequence current, so this means 1 over 3 IA plus IB plus IC, right? And we also know that I0 is equals to this is I0, sorry, and IN, the neutral, is equals to unbalanced current of IA plus IB plus IC. When we compare these two equations, we get the result as the neutral current IN is equals to 3 I0. 3 I0 means what? I0 plus I0 plus I0, and this is due to phase A, this is due to phase B, and this is due to phase C. Now this is phase A, phase B, and phase C. The neutral is serving as the return path for all the three phase currents. So if we draw the per phase equivalent model for the neutral, if we draw the per phase equivalent model for the neutral impedance is serving as the return path for all the three phases. So for each phase the current will be 1/3 when you are drawing the per phase equivalent. For three phase the neutral is carrying all the zero sequence currents. When you are drawing the per phase model, always remember that the impedance of the neutral as seen by the phase, each phase becomes 3 times the impedance of the neutral as seen by the phase. Whenever we are drawing the phase network, the impedance per phase network, the impedance of the neutral becomes 3 times as compared to the phase impedance, as compared to the actual neutral impedance. Why? Because 3 times in parallel for 3 phases, so the actual neutral impedance. Let's say that my neutral impedance, let's say, is xn. Then for per phase model, for per phase this neutral reactance would be 3xn. Similarly, if we have Zn, this is just write it as Z, then this would become thrice for per phase. Why? Because the neutral is carrying the current of all the 3 phases, so the impedance of the neutral as seen by the phase would be 3 times, right? And hence the voltage drop at the neutral Vn, we can say it would be equal to I naught 3xn. This is per phase voltage drop. This is the voltage drop. So the impedance of the neutral part is 3 phase of the original impedance. So when all the 3 phases combine, the impedance becomes the neutral current becomes equals to 5. Now coming towards the last topic of this video, it is regarding complex power in terms of symmetrical components. Complex power in terms of symmetrical components, right? So we know that the complex power, 3-phase complex power, is given as S3 phase is equals to the voltage times conjugate of current times 3, right? And these are the phase values. If we have the line values, then we have under root 3 factor with line and I, right? So now we also know that Vp is equals to VABC and IP, this is the phase value, right, is equals to IABC. So we can convert these values. So S3 phase, when we are considering all the 3 phases separately, then there is no need to involve this factor of 3. The 3-phase power will now be what? VABC matrix transpose IABC matrix, right? So what we can see, this would be ultimately VA IA conjugate plus VB IB conjugate plus VC IC conjugate, right? And now what we are doing is we are converting this. We know VABC is equals to what? A times V012, and IABC equals to what? A times I012. Transpose will be as it is, and conjugate will also be as it is. So when we open it, it becomes A transpose V012 transpose or we can rearrange it as V012 transpose A transpose A conjugate I012 conjugate, right? So when we multiply it, we find out that we know that A times A inverse is equals to 1/3 A conjugate times A and the transpose is same, right? And this is equals to I. A times A inverse is equals to the identity matrix. So this would be equals to 1/3 A conjugate times of A, right? And since A is a symmetrical matrix, we can say that A conjugate times A transpose. Why? Because A transpose is equals to A. Clear? Or in other words, we can say what we are saying, that 3I cross multiplication is equals to A conjugate times A transpose. So now the main equation, this one, let's name it as equation 1. This equation becomes as 3 phase is equals 3 times V012 transpose I 012 conjugate times I, and this I is the identity matrix. Let's represent this one also, right? Where is it? This one is also an identity matrix. So whenever any matrix is multiplied by identity matrix, we know the result is same. So this would be 3 V012 transpose I012. So this would be 3 V0 V1 V2 I0 I1 I2 3 conjugate circle V0 I0 conjugate plus 3 V1 I1 conjugate plus 3 V2 I2 conjugate. Now instead of finding the power of, in case of unbalanced system, instead of finding the power of separate phases, we can just find the sequence component and find the 3-phase component.